Let's take a quick look at some of the applications for condensing boilers, see how they might fit in with what we're doing. So here's an example of something that I call a no-brainer. So water source heat pump. Here's a water source heat pump system with a boiler and a closed circuit cooler specific in this case. And you might note this is an old-fashioned atmospheric boiler. It's been piped in with a constant bypass circuit setter to try to make sure that on this non-condensing boiler we kept the return water temperature above 130. Why? Because what is the operating range of a water source heat pump? It's 60 to 90 degrees, I think, would be acceptable to you guys. I'm sure you could stretch it either way, but let's just say 60 to 90 is a reasonable loop temperature to be looking at a water source heat pump. So you're saying to me, Chris, if I get down to 60 or lower, I'm going to turn the boiler on and add some BTUs. Absolutely. So what is your return temperature at 60 to the boiler? It's going to be cold. And that boiler is going to rain unless you do something to fix it. So what we did here was we put a bypass around it with a circuit setter and blended it to try to make sure that the return water temperature never got down below 130, because these non-condensing boilers, if you rained in them, you tore them up. It became a huge maintenance issue. So what are you getting at? I'm saying to you that a lot of these water source heat pump jobs out there that are 5 or 10 years old do not have condensing boilers, and they got maintenance problems. They got maintenance problems because you're raining in them, because the return water temps are getting below the 130 and you're tearing them up. I'm telling you, every water source heat pump job you know of should be changed over to condensing boilers immediately. Why? Give me 60-degree return water in a condensing boiler. I'll be 99% efficient. Give me a low load, modulate the condensing boiler down. I'll be 99% efficient. I can make a condensing boiler pay off on a water source heat pump job so fast you won't believe it. You should just stop what you're doing right now, get in the car and go find every job that's a water source heat pump job and look at the condensing boiler changeover. The paybacks are 2 to 3 years or less, and you're eliminating maintenance problems on top of that. Because I guarantee you these that are non-condensing, the older jobs, have got maintenance issues with their boilers because they're raining in their boilers and they're not designed to do that. Am I too strong with that? I don't think so. Every water source heat pump job should be a condensing boiler. It is the perfect application. Typical range, 60 to 90 degrees. It's always condensing. I don't care what you do, it's going to be condensing. And the vast majority of the time, they're at part load. Wow, what a perfect application for a condensing boiler. How about on radiant heat? Not a whole lot of that in Carolinas. We do have some in that warehouse at J&P Company, and it's very good stuff. This is where we're putting hot water tubing, hot water heat into the cement under the floor to keep the floor nice and warm. Now, obviously, there you don't want it real hot. So we're running 85 to 120 degrees, be typical range. So this application is always condensing, and most of the time at part load. So another great application for condensing boilers would be radiant heating. Just a fantastic application for it. I got one that may surprise you here. You know, the energy codes tell us to use outdoor air reset. So you got a 180-degree boiler at 10-degree outside design. Fine. It's a non-condensing boiler. What happens with an outdoor air reset schedule as you get the outside air going up? If it's 180 and, say, 10, it might be 130 supply at 50. Notice as the outside air temperature comes up, ASHRAE 90.1 2010 Energy Code says you shall have an outdoor air reset schedule and or variable flow, but outdoor air reset schedule to lower the supply temperature as it gets warmer outside. Now, tell me something. In your non-condensing boiler designed for 180 and 10 degree outside temperature, if you go on a reset schedule, say down to 130 at 50 degrees outside, what is your return temperature? Have you looked at the return temperature? Have you ever worried about the return temperature? You should be, because if the return temperature, if your supply is 130, what is your return? 110? 115? You're raining in these boilers. You're tearing them up. It's a huge maintenance issue when you put outdoor air reset schedules on non-condensing boilers. And people don't think about it that much because you look at the design. The design is 180. But where is it operating the vast majority of the time, and what's happening to the return water temperature? Is it getting below 130 at part load? The answer is yes. So you're raining in the boilers, you're tearing them up, you got maintenance issues, and a lot of people not even aware that's what's causing it, and they're blaming the boiler vendor. It's not the boiler vendor's problem. If you rain inside of a non-condensing boiler and tear it up, that's not a warranty issue, or should not be a warranty issue. It's a maintenance issue because it's raining in a boiler and the boiler's not designed for it. What a perfect way to solve that problem with what? A condensing boiler. Put a condensing boiler in there. You can still have your reset schedule. And now if it gets to 130, 110, 120 on the return side, who cares? I don't care if it goes to 60 on a return. What happens? Efficiency goes up. Now you're paying for it. So I'm telling you, on new applications this day and age, even with a supply temperature as high as 180, you want to look at condensing boilers to protect that boiler when you are at part load and the return water temperatures get below 130. It's a perfect way to solve those maintenance issues. Driving all this home, I think you need to slow down sometimes and look at a typical heat exchanger, air to hot water heat exchanger. And this is a sensible heat exchanger. Let's see what happens with a typical heat exchanger. So the bottom plot here on the horizontal axis is percent design flow. And the percent heat transfer is on the other side. In other words, the vertical axis is how many BTUs you're getting out as a percent, and the horizontal axis is percent flow. Now the red line is kind of the top showing you overflowing, you didn't gain a whole lot. Let's look at 100% flow, you're going to get 100% BTUs. Everybody see that? So 100% flow, 100% BTUs. I got my design delta T, whatever it may be. This is a sensible coil, not a latent now. Sensible, typical, sensible heating coil, hot water to air, hot water heating coil. Look at 50% flow. How many the BTUs do you get? Roughly 90. So I cut the flow in half, and I'm still getting roughly 90% of my sensible heat. Look at 25%. At 25% flow, how much of my BTUs am I getting? Oh, roughly what? 70%? So what are you telling me, Chris? I'm telling you, as you reduce the flow, that the heat exchanger is not linear. In other words, I'm getting 90% of the BTUs at half flow. So if I cut the flow in half and I'm still getting 90% of the BTUs, what's happening to my delta T in theory? Going up. Do you see the delta T has to go up to balance? So in a heat exchanger that's modulating down, the two-way valve is shutting the flow down a little bit, the delta T should go up. Wow. Going up to higher delta T means what? That means my return water temperature is colder. That means my condensing boilers are more efficient. I like that. How are we going to make sure it happens? Maybe this is a good application for this pressure independent control valve, those PIC valves, which you talk about later, and this is why. We want that big delta T. We want the water as cold as possible. The colder water you give me to my condensing boilers, the higher my efficiency. Not a bad way to go. This is an outdoor air reset schedule. Kind of jumped ahead as usual. This particular one is set for 0 degrees outside air, 180. My return would be well above 130. But at 60 degrees, my supply is 100. And my return is well below 130 because my supply is, and I'm running in a boiler. Typical outside air reset. I think you kind of got the message. So let's kind of summarize some comments on putting in new condensing boilers and some applications. And again, this is a repeat of things we said, but I think they're so important to all the condensing boiler applications you get into that you need to be aware of. First of all, increase the delta T. Don't go with 20 degrees. There's nothing wrong with 20, but the higher delta T's make a lot of sense. They give me colder return waters. My boilers are going to be more efficient. It cut my pipe sizes down, and I don't like this sometimes, but it cuts my pipe sizes down. So I'm seeing most designs probably about 40-degree delta T, to be honest with you, on hot water heating now. I see some at 50, some at 30, but there's nothing wrong with it. We're going to 40, and you might start thinking about it. Balance is more critical. If I'm cutting the flow rates down, I've got these small loads I'm trying to handle, I've got to make sure I get them balanced. And maybe it's not a bad place to look at a pressure independent control valve to make sure I'm getting those high delta T's. Especially when I modulate down, I should have my delta T's beyond design. That's good. I want that cold water. Look at your design heat transfer on your hot water heating coils. you're going to have lower supply temperatures because you're trying to make sure you get the return temperatures down. And you may have to change the sizing of your heat exchangers, and you may look at the static pressure across those heat exchangers that may or may not impact your fan power. Consider system supply temperatures strictly from the standpoint of the fact they got to come down. We want to design on return, but don't forget the impact on the supply and how that's going to size your hot water heat exchangers. We want to make sure our design maximizes the number of hours we can get low temperature return water. In other words, we want the water as cold as possible, as many hours you can give it to me. That's going to give you the most efficiency. That's why we're doing it to begin with. This efficiency optimization boiler staging is a great idea. And real simple. All that says is I'd rather run 3 boilers at 33% than one at 100. I'd rather run 2 at 50 than one at 100. And you may want to cycle your boilers, so you want to get equal runtime on your boilers. So equal runtime on your boilers, and do what I just said. You got an efficiency optimization schedule to do that. Most of these vendors can supply you with a factory mounted efficiency optimization program that would do this. And I would strongly recommend whatever brand of boiler you want to buy, specify that you go to one of those systems. I really think so. If you're not going to do that, get yourself a good control vendor who can do the same thing and meet that criteria I gave you about making sure you're putting boilers online, multiple boilers online at low fire to get that efficiency up. And it kind of says the same thing as that last statement. Increase the efficiencies with multiple boilers. I really would prefer to be running 3 boilers at 33% than one at 100. And keep that in mind when you specify them and how you buy them. Have a great day. Thank you very much.